All right, let's analyze three different types of bonds, shall we? And let's take a look at what we have to use here to our advantage. We've got some electronegativity values. Now these are values that have been determined. You can just look these up. But basically this is a number that tells you something's, it's an atom's attraction for electrons. Like how bad does it want electrons? So a bigger number like oxygen, 3.5. It has a strong electronegativity, which means it's attracting electrons with a much higher degree of attraction than, say, lithium at 1.0. Lithium doesn't really want an extra electron. In fact, lithium would like to get rid of an electron. It doesn't attract them well at all. So the higher number means it's attracting electrons, and don't forget, electrons, it's in the name here, electrons are negative. Okay, don't forget that point. Electrons are negatively charged particles. Okay, now, what we're going to do is analyze possible bonds. Say, for example, between a phosphorus atom and a boron atom. How much are they going to, how willingly will they share with the other atom? Will they share electrons equally? Because they're probably going to share electrons. They both want it. If I look over here, I can see boron has a value of 2.0 and phosphorus has a value of 2.1. So phosphorus wants an electron a little bit more, but not that much. Okay, they're going to end up sharing electrons. And this is where we would draw Lewis structures for such compounds. Now, let's just kind of walk through the three different types of bonds we're going to be dealing with. Nonpolar covalent means they're sharing electrons, and it means they're sharing electrons basically equally. For all practical purposes, they are equally sharing electrons, like two twins. Okay, the electrons spend just as much time on one atom as they do on the other. They move around, but they're not hogged by one atom or the other. Polar like opposite poles on a battery or opposite poles on the Earth. Polar means we have oppositely charged ends. Okay, not completely charged. We're going to get to that in a minute. But it means that one side of this molecule is kind of hogging the electrons. It's keeping the electrons more for itself. It's a little bit stronger, and it's attracting those electrons more, and the other one kind of loses it part of the time. It doesn't get to hang on to the electrons as much. And in order to do that, they must stay really close to each other, and we call that a polar bond. Okay? Ionic means, hey, one of these is so much stronger than the other that it just rips the electrons away and steals it. Okay, so this is stealing electrons, this is sharing electrons perfectly equal, and this is something in between where one's hogging the electrons from the other. Now let's analyze these based on the numbers. So the first thing we're going to do is look up these values. Okay, phosphorus we said is a 2.1, boron is a 2.0. Okay, the first thing you should recognize is those are really close to each other. 2.1, 2.0. Now, to figure out what type of bond it's going to be, we're going to find the overall difference in electronegativity. Remember that triangle means change in or difference between. So the difference in electronegativity here, if I do 2.1 minus 2.0 is 0.1. That's almost nothing, okay? That is this situation right here. I know this number tells you phosphorus is a little bit stronger, but for all practical purposes, it isn't that much stronger than boron, so it shares the electrons pretty much equal. So much that this atom is basically neutral. I'm sorry, this molecule is basically neutral. It doesn't have a positive end or a negative. We don't have to write those zeros there, but I'm just letting you know it's basically the same on both sides. One side isn't negative and one side isn't positive. The electrons just move around and spend as much time on one side as they do on the other. Okay, it's all equal. Now, let's take a look at how that, so we would label this as nonpolar. Nonpolar covalent. Okay, it's a nonpolar bond. Now, we look at carbon and oxygen. Let's look up their numbers here. Carbon is 2.5, and oxygen is 3.5. Here, there's a pretty big difference. The difference in electronegativity is 3.5 minus 2.5. Notice I'm just taking the big one minus the little one. It doesn't matter which order you do this in. It's like absolute value. I get a value of 1.0. Now 1.0 puts me in this category right here. Okay, it's between 0.5 and 1.9. That means there is enough of a difference to be able to tell. Oxygen is substantially stronger than carbon, so it's going to hog the electrons. It's not strong enough to just rip the electrons away from carbon, but it keeps them more of the time. So they spend more time on this side of the molecule than they do on this side of the molecule. And what that produces is an end over here that's kind of negative, because remember, electrons are negative. Okay, it's kind of negative where they spend more time, and it's kind of positive over here. Okay, we call that a partial charge. So we're going to put this little Greek letter sigma with a negative sign. That means it's partially negative. It's kind of negative. It's not completely negative all the time, but it's kind of negative on the right side, and it's kind of positive on the carbon. How do we know which one's which? The stronger atom will hog the electrons, which are negative. Electrons are negative. Don't forget that. So we have these partial charges on polar compounds. Polar bonds will have these partial charges. Non-polar bonds will not. We don't need to put those there. They're just totally neutral. We don't have to worry about it. And our last one here is lithium and oxygen. Now lithium has a really low number because it's a metal. It doesn't want to gain electrons in the first place. Okay, oxygen really does. So when I subtract those, I get 3.5 minus 1.0, and that's a value of 2.5. That's the difference in the strength of electronegativity. That's a big difference. In this case, oxygen is so much stronger than lithium that oxygen just rips them away. And this becomes an ionic bond. Okay. Ionic means they trade or just transfer electrons. So oxygen just tears the electrons away and keeps them. So that means this side is completely negative and this side is completely positive. Okay. So the way in chemistry we kind of designate this is if you see a positive or negative, that means it's completely charged from electrons moving from one thing to another. Partial charges means they're just spending more time over here, but they don't completely leave the other atom. And then no charges means it's neutral. They're essentially like identical twins based on the numbers. They're close enough. Okay, and those are the three types of different bonds you may run into. We use the electronegativity values to figure out what's going to happen. And look, these breakdowns, you're going to see slightly different things depending on the book you look at. Some of them will have these categories in slightly different places. It's like a rainbow. It's hard to tell where blue changes to purple. Okay, it's kind of like there's this sliding scale of everything. And chemists and physicists have to essentially set up some parameters and say, listen, anything with 0.4 difference or below, we're going to call that nonpolar. Okay, anything with 0.5 and above, we're going to call that polar, just because we have to have a place to sort of categorize it and cut it off. But it's all like a big continuum where one thing, it's all how much more polar is something than something else. Okay, so something with a difference of 0.5 is barely polar, and something with a difference of 1.9 is really polar. So everything is compared to something else. These are just some general breakdowns you can use to kind of give a good target to figure out what sort of bond will probably happen.